Where we left off on Monday was we had just done a source to generation scheme, which we observed increased the output resistance of our current mirror. But the trade-off was that we had significantly reduced headroom. And so what we're going to be talking about today are options for us to increase our headroom while still getting that increase in output resistance. So our third option for enhancing the behavior of our current mirror or making it behave more like a ideal current source is to create a cascode current mirror. So with a cascode current mirror, all we are doing is the exact same thing that we just did with the source to generation, except that instead of using a physical resistor, we are using a transistor instead. So if we have if this is transistor M2, and we'll worry about how it gets biased in a moment. I'm going to call this transistor M4. And I want to figure out what this output resistance is. And so how we are going to approach that is, instead of drawing a big, huge, ugly, small signal model and figuring things out, we're going to be a little bit smarter about it. And we're going to look in through this terminal. I'm going to call this guy right here R out prime. Because what's going on here is that transistor M4 is acting like that resistor R sub S. So if we know what the resistance that we see that transistor M4 looks like, we can just throw that relationship into our previous equation without having to do all the big small signal model analysis. Okay. So transistor M4 is connected to a biasing network at the gate. So that means its gate is going to be at AC ground. Here's the gate of transistor 4. Here's the source for transistor 4. And we can easily see that it's tied directly. Here we're going to have GM4, VGS4. So this voltage here must then be VGS4, since it's a potential difference between the gate and the source. Here we have our channel length modulation resistance, R out 4. Here's the drain of transistor M4. And here is the output terminal that we are looking in to find R out prime. So, Albert, I'm going to pick on you. What is VGS4 here? All right, so what is the voltage associated with the positive polarity terminal of VGS4? Ground, right? What's the voltage associated with the negative polarity terminal of VGS4? It's also ground. So that means VGS4 is what? Yeah, 0 minus 0 is equal to 0. So since this voltage VGS4 is 0, what does this current source do? So whatever GM4 is multiplied by 0 means that it doesn't supply any current, right? So all we see is this resistor R out 4 because the current source does nothing. So this R out prime is simply R out 4, which means that the output resistance of this stack or cascoding of transistors is GM2 R out 2, GM2 R out 4, sorry, R out 2. So we get the exact same scaling that we had earlier. We're multiplying that resistance R out 2, but we're now scaling it by a factor of GM2 R out 4, where that R out 4 is just replacing RS that we had in our equation from our resistor-based degeneration technique. Okay. Now, this is going to look like GM R out squared, assuming transistors M1 through M4 are identical. So we have made an assumption here. Can anybody tell me what this is or what our assumption is? It has something to do with this resistor right here, R out 4. That's true with M1 through M4 being identical, so that we can just replace R out 4 with R out 1, 2, 3, and they're all the same thing. But we've already listed that assumption. There's another assumption here that's very, very important. In our small signal model, this resistance only appears because of channel length modulation, which is only a thing when our transistor is in the saturation region. So we are assuming that M4 is biased in such a way for it to be in saturation. So I'm going to write that down here. For this to work, M4 must be in saturation, which means that VD4 sat will be equal to VGS4 minus VTH. And we'll revisit this guy momentarily. Right? So we get an increase in output resistance under the assumption that our transistor is in saturation, but this absolutely impacts what's going on in the DC side of things, because it tells us, it puts restrictions on how we can bias this thing, because we have to force that transistor to be in saturation, right? So overall, our system should look like this, right? Here we have VDD and our reference current. Since we have stacked transistors on the right-hand side, or the output side of this thing, we're going to have to stack or cascode our transistors on the left-hand side as well, because we need this guy to be symmetrical for it to behave well. And should have something like this. And I am going, let's call this guy, sorry, M1. This is still M2. And now we are degenerating M1 with a transistor M3. We are degenerating M2 with a transistor M4. And for our current mirror, we expect to have the gate and the drain of M1 tied together, so that's still going to happen. And I'm going to tie together the gate and drain of M3 as well, so that it is a perfectly matched and symmetrical network. So effectively, we've loaded the current mirror formed by M1 and M2, or we've degenerated the current mirror formed by M1 and M2 with another current mirror, or we can think about it as loading the current mirror M3 and M4 with a current mirror, same exact things. So a couple of different voltages that we're going to have to look at. Let's call this guy VG1, this guy here VG3. The understanding here is that VG1 is the same as VG2. It's the voltage present at the gate of transistors M1 and M2. VG3 is the voltage present at the gate of transistors M3 and M4. Let's call this voltage right here VD4, and let's call this voltage right here VD2. All right. So if all transistors M1 through M4 have the same W over L ratio, then VGS1 through 4, right? So all of our VGSs will be VTH plus VDSAT. So what this statement means is that if all of our transistors are identical, they're all carrying that exact same current I reference, right? So I reference has to flow through M1, and since if it flows through M1, it has to flow down through M3, then we know that M1 and M3 are carrying the same amount of current. Since M2 should be mirroring what's seen in M1, that means M2 is carrying IREF, and I4 must also carry IREF. So all of our transistors are carrying that same current. So they should all have the exact same gate source voltage. So this is going to be VTH plus UN Cox W over L, and then twice IREF in the numerator. I'm probably just going to call it VDSAT from here on out for a little bit, but just to refresh you. All right, so what is our voltage VG3? Let's start there. So VG3, since nobody's saying anything, has to be the same as because our source is at ground, right? So that means that VG3 is at a potential exactly VTH plus VDSAT above ground. Everybody okay with that? What about VG1? Anybody have any thoughts about how we might figure this out? VG3 plus VGS1. Yeah, just using Kirchhoff's voltage law, right? So let me make it potentially a little bit more obvious. Here's VGS1, right? And so using Kirchhoff's voltage law, we could say that VG1 with respect to ground is VGS1 plus VG3. I agree 100%. So since VGS1 is the same as VG3, this is just going to be twice VTH plus VDSAT. Everybody okay with that? So what is our voltage VD4 going to be? What bias voltage do we see at the drain of transistor M4? Exactly right. So we have a voltage here, VGS2. So that means VD4 has to be VG1 minus, excuse me, that should be VGS2 or VTH plus VDSAT. So let me ask you guys a question. Is this voltage less than, equal to, or more than what we need to keep transistor M4 in saturation? More than, because to keep it in saturation, it just needs to be at exactly VDSAT, right? So this contribution right here is going to eat up a little bit of headroom, right? But it's going to be less than what we saw with the resistor when we had a large value resistor, okay? So we have made some improvement. So I just want to put a note here. VD4 is larger than it needs to be keep M4 in saturation. So now that we know all of those other biasing voltages, what is the minimum voltage that can occur at the drain of transistor M2 with respect to ground to keep that guy in saturation? Pardon? So if VD2 were at VDSAT by itself, that means it would be at a lower potential than VD4, and so we'd be deep, deep, deep in the triode region. It actually needs to be a VDSAT higher than what we have at VD4 in order for it to be in saturation, right? Which would be VTH plus twice VDSAT. So just as a quick aside here, with using a resistor, we saw that VD2 minimum was VGS1 plus IREF times R minus VTH, right? So which of these two quantities do you think is going to be a smaller voltage, generally speaking? It's going to be this guy right here, right? VD sat for most values. So it absolutely depends on the current that we're passing through it. But we're going to see that VD sat is going to be smaller than IREF times R because we have a strictly linear relationship here, but we have a square root based relationship here. So this guy's going to be a little bit smaller. So we have increased our output resistance, right? And we have gotten back a little bit of our headroom by having a smaller minimum voltage that needs to appear at the drain of transistor M2. So how can we even more efficiently design this guy, right? So if I want to make VD4 as small as possible, what voltage do I need to change? So I want, excuse me, yeah. So right now, that's why I wrote my note down here, VD4 is larger than it needs to be to keep M4 in saturation, right? So if we can make VD4 smaller, we know that VD2 is also going to be smaller because the minimum value for VD2 depends on the value for VD4. So how do we make this guy smaller? Changing the threshold. So changing the threshold voltage means we're going to have to change a lot of different things about our transistors, right? Can we, so once our transistors are made, they have effectively a fixed threshold voltage unless we start messing around with body effects and stuff like that. And that's actually only going to make the threshold voltage larger. Exactly right. Change VG1, okay? So we're now going to develop a scheme. We're changing VG1. And so this is our fourth option, and this is going to be the last one that we discuss in this class. And it's a doozy. All right. So option 4 is what's called the wide swing, or alternatively, high swing cascode current mirror. All right. So what we're going to start with look similar-ish to what we've been dealing with, but we're going to talk about some very specific choices that we're going to make here. So let's start with a transistor M1 and a transistor M3, because we have absolutely observed that cascoding our transistors got us a large output resistance. Call this guy M3, this guy M4, and we know that our gates are going to be tied together. So let's talk about what we are trying to do here, okay? First, we want VG1 to be biased low enough that VD4 is equal to VD sat. So that's our first objective, right? VG1 is low enough so that VD4 is exactly equal to VD sat. Second goal is that M2 draws a current of IREF. So we want this thing to continue to act as a current mirror. Very important caveat for this current mirror. And thirdly, we want, so let me label these guys real quick. Let's call this guy right here G1. Let's call this guy right here VG3. Let's call this guy right here VD4. Let's call this guy right here VD2. So we want VD2 to be as small as possible to maximize headroom. So to satisfy these three conditions simultaneously, we're going to have to get a bit creative. Okay. So the first thing that I'm going to do is, oh, sorry, and this current should be IREF. I'm going to tie the drain of transistor M1 to the gate of M3. All right. So that's going to force VG1 to be smaller. We'll talk about that in a moment, but it gives me a little bit of a dilemma because now that quantity VG1, well, let me think. So VG1 isn't at a fixed value anymore. So to force that to happen, I'm going to add another transistor. All right. So let's say that we have another current mirror, effectively, IREF let's call this transistor M5. And what it does is bias transistors M1 and M3. And because it's a current mirror, simple one, I'm going to put this guy right here. And this parameter, W over L5, is going to be critically important to making this work. So I'm going to go ahead and make note of it now. Okay. So this is what our wide swing current mirror looks like. So before we get into our DC analysis, what is our output resistance of this guy going to be? Or let me ask the question in a slightly different way. Will the output resistance change at all from our cascode current mirror that we analyzed first for today's class? Short answer is no. Everything to the left of the gates for M3 and M4 is just biasing stuff. It's generating specific DC voltages, right? So we are still going to get exactly GM R out squared if M1 through M4 are identical, right? So we get the exact same output resistance as our previous deal. Now we're just trying to clean up our headroom requirements a little bit, all right? So utilizing this connection, what can we say about the voltage VG3? So that's the gate voltage for transistor M3 and transistor M4. It is exactly equal to VGS3, which will be VTH plus VDSAT, right? We should see that that transistor M3 still carries that current of IREF. M1 is going to carry it as well, but that's where things are going to get a little bit wonky as to figuring out how exactly this guy works, okay? So to make VD4 equal to VDSAT, let me write this down. We need VG1 to be equal to sorry, I have two M3s here. I apologize. Yeah, 1, 2, 3, 4. There we go. VG1 to equal VGS2 plus VDSAT, which will be VTH plus 2 VDSAT, where again, transistors M1, M2, M3, and M4 are all equal. Does this make sense here, right? So if VG1 is equal to VTH plus 2 VDSAT, Kirchhoff's voltage law tells us that VD4 will be exactly equal to VDSAT. All right. So if this occurs, then VD3 will be VG1 minus VGS1, which will be exactly equal to VDSAT. So that means transistors M3 and M4 will both be biased on the edge of saturation, right? Any lower and we hit triode region. So how do we make all this stuff happen? That's the million-dollar question. And it all comes from sizing that transistor M5, okay? So to make all of this work, we need to size M5 such that VG1 is equal to VTH plus twice VDSAT, all right? So let's look at what we've got going on here, all right? So this transistor M5 is going to have some current flowing through it, or actually it's going to have exactly I reference flowing through it. And that simple feedback loop then is going to force a particular voltage VGS5 or VG5 to appear at the gate terminal of transistor M5. That same voltage will appear at the gate of transistor M1, right? And that voltage VG1 is what we're trying to force to be this guy right here. But obviously, VGS for transistor 5 and VGS for transistor 1 can't be the same thing, because VG1 needs to be at a higher potential to keep everything else biased at the edge of saturation. That's why we have to resize this guy, okay? So we can say that VGS5 will be VTH plus the square root of 2 times our reference current divided by UN Cox W over L for transistor 5, right? We're forcing a current of IREF flowing through it, and so that feedback system winds up giving us that voltage at our gate of transistor M5. Our constraint here is that VG1 is equal to VTH plus twice VD-SAT for transistors M1 through M4. And so this is going to be VTH plus 2 times the square root of 2 IREF UN Cox W over L transistors 1 through 4. So since VG1 must equal VGS5 for this thing to work, that means that square root of 2 IREF over mu n Cox W over L5 has to be equal to twice the square root of twice IREF mu n Cox W over L for transistors 1 through 4, excuse me. So what is the relationship between the aspect ratio of transistor 5 and the aspect ratios of transistors 1 through 4? Pardon? Okay, smaller, but how much smaller? Exactly 4 times smaller, right? W over L5 is thus equal to 1/4 of the width over length or aspect ratio of transistors 1 through 4. Okay. So, oops. If M5 is sized to be W over L5 is equal to 1/4 W over L 1 to 4, then VD4 is exactly equal to VD sat. VT1 is exactly equal to VTH plus 2 VD sat, and VT2 minimum will simply be twice VD sat. And I'm leaving this without proof because logically, if VD4 is at VD sat, then VD2 just needs to be one VD sat higher to keep it there, but we could do KVL loops and all that kind of crap to prove it as well. So this scheme, the wide swing cascode current mirror, makes transistors M3 and M4 biased at the edge of saturation, giving us the smallest possible value for VD2 while maintaining that output resistance of GM R out squared. Okay. So that's all I wanted to talk about today. We're going to do a review of cascode amplifiers and all that kind of stuff starting on Friday. One thing that I want to mention to you guys, all of this derivation is based on the fact that transistors M1, M2, M3, and M4 are all of the exact same size. You might see it in some other textbooks with a little bit different derivation where they're effectively saying M1 and M2 might have a different size than M3 and M4, which then implies that M5 would also have a different size. I don't want to go through that nightmare. Okay, so let's just leave transistors 1 through 4 the same size and make the math much easier than it would get if we started jacking around with the sizes too much. Okay, it'll wind up being, like you'd say, W over L is the size of transistor M3 and M4, and M1 would be a fraction of that. And so the size of transistor M5 would be, so what it winds up being here. So let's say this would be W over L divided by a factor of N. This guy would be W over L divided by a factor of N. Well, this guy winds up being W over L divided by a factor N plus 1 squared. Proving the math for that is ludicrous. I don't want to do it. Okay, so leave the transistors the same size and make that guy 4 times smaller, and you're good to go. Seems much easier. All right, that's enough out of me for today.